the idea of resistive motion, we can break the problem down into one of three types. Remember, resistance is always in the opposite direction to your motion because it's resistance. So it's like a force in the opposite direction to which you're travelling. That's another part of third law. They're balancing, the forces are balancing. Horizontal line, if we are travelling along the x-axis, so there's good old Bob, travelling, what forces are applying on this particle? Well, if I make the resultant force going to the right, I have a resistive force going to the left, always in the opposite direction. That's the only force. Because gravity is a purely vertical force. So there's no component of gravity whatsoever when I'm travelling horizontally. So I'll always end up with some sort of formula like this. Mass times acceleration is negative that resistive force. So I would divide through by the masses. I'd have some equation and I'd go and calculate that out. Okay. If I'm going upwards, that one we just looked at was an upwards motion, but it didn't take resistance into account. I'll define upwards, the direction I'm travelling, to be the resultant force. I will have a force due to gravity now in the opposite direction. I will also have a resistive force in the opposite direction. So the resultant force will equal all the other forces added together. So minus mg minus r, they're both negative because they're both in the opposite direction. And again, I would divide through by mass. I'd get some equation that I'd then go and play with. Notice, it doesn't matter we've added resistance in, the laws don't change. If they ask me a question about greatest height, it's still going to occur when the velocity is zero. I mean, that doesn't change. Case 3, going down. But because I want to define things in the direction I'm travelling, I'm going to make the resultant force going down. So actually going down will be the positive direction for these sort of problems. Gravity is still going down, but now resistance will be going up because it's going in the opposite direction to which I'm travelling. So I'll end up with this sort of equation. Force is equal to mg minus r. Divide through by the masses, get some equation, and away we go. Now in downwards velocity, we have a term called terminal velocity. It's basically when all the forces are in balance. So if all the forces are in balance, that means acceleration is equal to zero. So that's how you find terminal velocity, when acceleration is equal to zero. So I'm going to look at a question that was similar to the one that we just looked at, just not as complex. A particle is projected vertically upwards with a velocity of little u, meters per second, in a resisting medium. Let's talk about this thing called retardation. Assuming that the retardation due to the resistance is equal to kv squared. Now, the biggest problem people have with this is they tend to go, well, hang on, are we talking about a force or are we talking about an acceleration here? In reality, it doesn't matter because it's going to equal some constant times it. And so whether that constant involves the mass or doesn't involve the mass, it just makes it a different constant in the problem. So we're assuming retardation due to resistance equal to kv squared, and we'll see in a second whether I'm going to assume that's a force or an acceleration. We're going to find expressions for the greatest height and the time taken to reach that particular height. Okay, there's good old Bob. Resultant force, mx double dot. Going down, mg. Now they've told me kv squared, so there it is. I'm going to assume it's a force. Sometimes they'll even use the term retardative force or force due to resistance. They'll be very explicit about it, and then you know it is. But here I'm assuming that's a force, kv squared. Now I know when displacement is zero, velocity will be little u. So balance my forces out. Resultant force will be minus mg minus kv squared. This is what I meant. If you've ended up, say they said show acceleration was this. And you see how there's an m in the answer? So that's when I would assume kv squared is is a force. So when I divide through by m, it's still going to be there. If I had said kv squared was an acceleration, then the force would have been mkv squared. And then when I divided through by the m, there'd be no mention of m in the answer.
So we don't have the answer.
Correct. So I can do what I want. It just means my k, someone who assumed it was an acceleration will have a different k to my k. K over m is still a constant. And that's what I mean by it doesn't really matter. So you'll notice I'm using v dv dx for acceleration this time. Why is that? Look at the equation I've got. I've got acceleration in terms of velocity. So I want dv. I have dv to t. I could use dv to t. That's got a dv in it. But that would link velocity and time. That'll be useful maybe for the second one, time taken to reach the greatest height. But the first one is I want something that links displacement. So I'm going to use v dv dx. Divide through by v and turn it upside down. And I get mv on minus mg minus kv squared. So my expression for displacement, I'm doing it as a definite integral. Initial velocity was u. We're going up to when it stops, so a velocity of 0. V dv on mg plus kv squared. It's a log function. What's the derivative of kv squared? 2kv. So I want to create 2kv on the top, so I've just got derivative on function. Means my constant out the front now is m on 2k. You'll notice something else I did. I got rid of the negative, but I swapped the limits around as well. See how it now goes from 0 to u instead of u to 0? So I have log mg plus kv squared. This line here where I say log of mg plus ku squared minus log mg, you don't really need that line. You could go straight to mg plus ku squared on mg, because you know you can end up with log minus log. And log laws say I can bring them together into one fraction. And I've just rewritten that as 1 plus ku squared on mg. Okay, so there's an expression for the greatest height. So acceleration is equal to minus g minus km v squared, k on m v squared. This time I'm going to use dv to t because I now want to find the time it takes. So I want to link velocity and time together. So I'll use dv to t. Similar thing, turn it upside down. This time though, it's dv on mg plus kv squared. This is going to be an inverse tan function. So I don't really want kv squared, I just want v squared there to use the inverse tan. So I factorise out the k, but it means my mg changes to mg over k. And so when I integrate, remember with the inverse tan you get 1 on a out the front as well. So I've got root k on mg inverse tan, root k on mg v. We're going to sub in u, minus sub in 0. And there is an expression for the time taken. A body of mass 5 kilos is dropped from a height. Gravitational acceleration is g. Assuming air resistance is proportional to speed. That constant of proportional being 1/8. Find the velocity after time t. Okay, let's draw a diagram. I'm going down, so my resultant force is going down. Whether you leave it as m or you sub it in, they've told me the mass is 5, so I've made it 5x. Gravity going down now will be 5g. And there'll be air resistance going up of 1/8 v. 1/8 v. So 5x double dot is equal to 5g minus 1/8 v. Divide through by the 5, I've got my expression for acceleration. dv to t, velocity after time t. I want to link velocity and time together. So I'm going to use dv to t for acceleration. Turn it upside down. I'm doing it again as a definite integral. We're starting from a velocity of 0 because I'm going to just drop it. So initial velocity is 0, dropping it to some random velocity v. Once again, we have a log function in this case. So 40 log 40g on 40g minus v we end up with. So t over 40, Remember, we're trying to find the velocity in terms of t. So I now have to make v the subject of this. Undo the log, exponentialise both sides. There's a fair bit of algebraic manipulation in this one. Turn both sides upside down, so it's now e to the negative t on 40. And eventually we make v the subject, 40g outside of 1 minus e to the minus t on 40. The terminal velocity, a gift question. Remember, what did I say terminal velocity was? Good. There's another way of working out too. You can say as time approaches infinity. See, if I've got a velocity equation, I can also do it via limits with t approaches infinity. So either way will give me the answer. I could say acceleration is equal to 0. So I go back to the original acceleration formula, solve that, yes, I get v equals 40g. Or, because I have the velocity time equation, I can say, well, that'll be the limit of 40g, 1 minus, and we have our exponential. If you think of your exponential, e to the negative t will be coming down and approaching 0. And so I'd end up just with 40g. Either way, we get the same answer. Now I want to find an expression for the distance it has fallen after time t. So back to dx to t. Remember, we got dx to t is equal to 40g 1 minus e to the power of minus t on 40. So x will equal, this time to my limits, I'm starting with a t equals 0, going to some random time. Integrate 1, we get t. Integrate e to the minus t on 40, and there's our plus 40 e to the minus t on 40. Sub in t, sub in 0. And we get this beautiful expression there for the displacement. 4a, 4b, couple more out of Patel there.